Hello. So today I have a showcase for you, and I believe, I could be wrong, but I believe this is the first showcase I've done that is just a classic Sudoku. So this is something different. So the story behind this is Philip Newman uh, creates a classic pretty much, I want to say daily, and puts them in the Sudoku recommendations channel. He has software that hunts for uh, various puzzles that use a lot of advanced techniques, and he posts them, and a very niche group of people try to solve them because they're often extremely difficult. And this is certainly no exception. In fact, this was so interesting that I decided that it would be a good showcase of how you can even go about solving these really difficult puzzles. Now, whether or not you're going to find these techniques is something else. So don't feel bad if you don't. I certainly didn't. I struggled a lot on this puzzle and got nowhere. So do keep that in mind. If you do want to try the puzzle, feel free to. It's just normal classic Sudoku rules. It's called Chironex Fleckeri by Philip Newman, and that the title is a hint towards maybe part of the opening, although you may struggle even with that part. And it just gets worse from there. So don't feel bad if you are not able to make any progress, or if you have to bifurcate, or whatever you want to do to get this solved, and then come back and watch a very interesting path to get this solved. And the reason I definitely recommend watching is there's some very cool techniques done here, and I'm going to try my best to help explain how you might go about looking for this sort of thing. Now, whether or not that's successful, I have no idea, but I think it'll be a learning experience for myself and for everyone else to just try to go through that and see how successful that is. So again, please do give it a try. And again, don't feel bad if you get, a couple digits and then completely stuck, because that is probably what's going to happen. Some adventurous people might find even more and then get stuck. So let me know how you did, and then come back and watch this solve, because it is quite fascinating in my opinion. These solve steps were created by Philip. He released a Google Doc, which I'll also link below in the description, along with the links to the puzzle. And do feel free to check out his description of the solve as well. And I'm going to be kind of walking through that. So just to let you guys know, I will pull this on screen. I am not hiding anything. I am going to be referencing Philip's awesome document here for the solve path. So this is just for people who want it visually instead of trying to read through this and understand it that way. So whichever you prefer. And I will get started. So I'm going to have this off screen. Just if I look this way, that's what I'm looking at. So yeah, I'm going to get started now. All right, so we're going to start with some really basic Sudoku just to get a few digits. So we have these two sevens here that look into box 5. That gives us this 7. We also have these two sevens looking into here, and this 7 looking here into box 6. So we have another hidden 7 here in box 6. This 8 looks over into box 1 along with this 8, which allows us to corner mark 2 8s here, which then look over into box 3 along with this 8 and this 8, allowing us to actually place an 8. These 2s interact with box 9, letting us corner mark 2s here, which then see up with this 2, and allow us to corner mark 2s here. All right, and that is basically as far as you're gonna get. What I did after this is I fully marked the grid with center pencil marks, and I still didn't find anything useful. I then put it into my solver just as sort of a giving up point, and my solver did not have a nice path for it, so that's why I was very excited that Philip finally posted his solve path, because it was very interesting. And so there's 2 ways to move forward from the start. I'm going to go with kind of the traditional way, and then I'm going to show an alternate way, which is going to be very interesting as well. So this pattern is, if you look, especially with the 7s that we placed, we get this kind of block of digits here, as well as this kind of corresponding block of digits here. And I'm just going to color that in a nice blue color here. So what we can notice about this block of digits, and I guess we can also kind of add this to the mix, where we're missing one cell here. We're missing one given here. But otherwise, this entire block of digits is only made up of 2, 5, 6, 7, 8, and 9. So more specifically, it's missing 1, 3, and 4. So we don't have any 1s. We have 2. We don't have any 3s. We don't have any 4s. We have 5, 6, 7, 8, and 9s. And you can see that that's true. Now this cell could be some of those digits, but we'll get to that in a second. So what that automatically does is if we look at the blank spots here, which I can color in green, that's going to form a jellyfish, except it doesn't because we don't know what this cell is. If we knew this cell was also from this set of digits that weren't 1, 3, and 4, then yes, we would have a jellyfish. And so the jellyfish is restricted on the columns. But we're going to pretend that this blue cell is not a 1, 3, or 4. And if it weren't, then we'd have a 1, 3, and 4 jellyfish. And I guess to point out, this is 5 locations in the column. But if you notice, we have a given 1 here, a given 3 here, and a given 4 here. So we're going to have 3 different jellyfishes that are slightly different, that affect slightly different rows, although this row and this row will be in common. That will, if this cell were not 1, 3, and 4, would eliminate 1s, 3s, and 4s from definitely all of these cells. None of them could be 1, 3, or 4. And then also, let me make that orange. For the 4s, we'd be eliminating 4s from here. For the 1s, we'd be eliminating 4s would also eliminate from here. The 1s would eliminate from all but this bottom row. So we'd get rid of this bottom row and we'd eliminate 1 from there. In addition to the oranges, of course. And the 3s would eliminate from all 4 rows except for the one with the given 3, right, which already has 3s eliminated. So that's 3 different jellyfishes on 1, 3, and 4. And that, again, that's spottable because we kind of have this block of givens. And so that you might be able to spot that. But the problem is that it's not actually 3 jellyfishes because we have this sort of extra cell. Now, this extra cell is sometimes called the fin. And the reason for that is, let's imagine for a second that it is a 1 of 1, 3, or 4. Let's call it a 1. Well, in that case, we don't have a jellyfish, but 1 is still eliminated from this cell here. And if it's not a 1, if it's anything other than 1, it's a 3, 4, or, I don't know, it can't be 5, obviously, but maybe a 7, right? If it was any of those digits other than 1, then we do have a jellyfish, because this is not a 1, so 1 now actually is limited in all 4 of these columns to these cells, with the given 1 down here, obviously, making it a jellyfish. And that still eliminates a 1 from this cell. So you can kind of think of it like a Y-wing, if you're familiar with the Y-wing, or it's a similar concept where this cell has 2 states to it. It's either a 1, in which case this isn't a 1, or it's not a 1, in which case we have a jellyfish, and this still isn't a 1. So we can't talk about any of these other orange cells, but what we can talk about is this cell in particular cannot be a 1, 3, or 4, because we either have a 1, 3, or 4 in this cell, eliminating it, or we have the various 3 jellyfishes that form that eliminate 1, 3, and 4 from this cell. So what can this cell actually be if it's not 1, 3, or 4? Well, it could be a 2, can't be 3 or 4. It sees a 5, it can be 6, and it sees a 7, 8, and 9 in the row. So it's actually limited to 2 and 6. And so that's one way that you could kind of move forward to the next step by limiting that cell to 2 and 6. That's actually, you might get a few other eliminations if you fully grid it, but that's the important cell to move forward. Now, instead of moving forward, I'm going to show you an alternate way that we could have gotten this same deduction. So I'm going to keep that cell marked orange, but I'm going to get rid of this highlighted jellyfish. And instead, what I'm going to do is I'm going to use set theory. So I guess let's start from scratch on this set theory. Now, what is set theory for people who don't know what it is? And by the way, if you are not familiar with the jellyfish, now I have not gone over the fin jellyfish, which I just did here. If you're not familiar with the jellyfish and you got very confused by this, I do have a Learn to Love Sudoku video where I go over both the swordfish and the jellyfish, and I will link that a card up there or up there. I don't know which direction it is, but a card should appear, and you can click that, and that will teach you all about the swordfish and jellyfish. So hopefully that'll give you more context. But let's go over set theory. So what is set theory? Well, set theory is a complicated and difficult to use theory, but also not that difficult to understand. So it's fairly understandable if someone points out a specific thing, but it is difficult to use because there's so many options for it. But I'm going to go over the basics, and with this example, I will go over the basics and go slowly on that. So the basic idea behind set theory is that we take sets of 1 to 9 and we sort of add and subtract them in particular ways. So just as an example, let's take this column here and let's highlight that blue. So with that column blue, I know that the blues contain the digits 1 through 9. Now this is the simplest form of set. I'm going to take this row here and let's highlight that one red. And notice that this cell is both blue and red now. So the reds are the digits 1 through 9, and the blues are the digits 1 through 9. I mean, hopefully what I'm saying is incredibly obvious to you, because it should be. I'm not really telling you any secrets. And so therefore the blues and the reds contain the same exact digits as each other, which is specifically one of each of 1 through 9. Now what I could do is I could remove this cell here from both the blues and the reds. And what happens is there's only one digit in that cell. And so I've removed that same digit, whatever it is, from both the blues and reds. So we can still say the blues and reds are the same 8 digits as each other. And they'll be missing whatever was in here. And so now I can repeat this process and I can just add another column. Let's just add this column here. And so now what we can say is the blue, and let's just, for now, let's re-add this just to avoid confusion. The blues are 2 sets of 1 through 9, and the red is 1 set of 1 through 9. So I'd better add another red to balance that out. And so now the reds is 2 sets of 1 through 9, the blues 2 sets of 1 through 9. And so again, I can remove these overlaps, and I can still say that the blues and the reds are the same digits as each other, because they both started as the digits 1 through 9, 2 sets of them, and I removed the same 4 digits from both of them. So wherever they overlapped, I removed, and what's remaining is the same in both sets. So now I'm just going to repeat this. I'm going to undo removing that. I'm going to repeat this by adding one more row of red, and I'm going to add these 2 columns of blue. And then I'm also going to make sure I get this right here. Yeah, I'm going to add these 2 rows of red. Let's get rid of this orange for now. So we are unbalanced at this point. But what I can do is I can remove the overlap. And you can see why I chose these particular rows, because now we have this same block, this block that gave us the 3 jellyfishes. I have that same exact block highlighted in blue. And now what we can say is the blues are, all of the blues are in the reds. And in addition to that, the reds have an extra set of 1 through 9. And the reason for that is the red started with 5 sets of 1 through 9. That's these 5 rows. Yeah, these 5 rows. And the blue started with 4 sets of 1 through 9. And then I removed just their overlaps from both, which removes the same exact digits from both. And so now the red is blue plus a set of 1 through 9. So in order to balance this out, now you can do stuff with this in certain situations. There are definitely uses of unbalanced sets. But in this case, we want to balance out the set. So we need to pick some set of 1 through 9 to add to the blues in order to kind of balance out so that they're exactly the same digits. And what we can choose is we can choose to do box 7 here, because this if you notice, this is where the fin was. But I'm actually adding this to blues. So if I color this blue, I can signify that this one was double added, just maybe by making it purple instead of blue. So that's double added. And then this overlap, the blue, we're saying blue is added and red is subtracted, for example, they zero out. Remember that anything that was both blue and red, we can just remove. So now what we can say is the blues and the reds are the same exact digits, except this purple cell is double counted. So whatever digits in this purple cell is in the reds twice. So now what we can do is we can look at blues versus reds. And if you remember, in these givens that we've marked blue, we're missing 1, 3, and 4. And in the reds, we actually have a single 1, a single 3, and a single 4. Which means that a 1, 3, and 4 one of each at least have to be in the blues somewhere. And notice the only blues that aren't filled with a given are in box 7, specifically this L shape in box 7. So it doesn't matter that this one's double counted, because we have to fulfill a 1, 3, and 4 somewhere in the blues, and the only place they can go is in box 7. So if I were to place a 1, 3, or 4 in any of these white cells here, I would no longer be able to fulfill that equity, and I would break the puzzle. So these cells cannot be 1, 3, and 4. And notice that this cell here was the one that our 3 finned jellyfishes removed 1, 3, and 4 from to make 2, 6. And so what we can actually do is we can actually we can do something even stronger than what the finned jellyfish told us, which is that 1, 3, and 4 must be only in this box, must be only in where these blue cells were. And we don't even care that this one's double counted. And so now this one can't be 1 and this one can't be 4. But we know that 1, 3, and 4 are present in these blue ones. And so now we can, again, mark this as 2 or 6, because if you remember, it can't be 1, 3, or 4, and it sees 5, 7, 8, and 9 already. And of course, we could mark these as not 1, 3, or 4 as well, so we may as well fill those in. So they can be 2, 5, 6, 7, and 8. This one can't be 5, this one can't be 4. Oops, I typed the wrong number there. Oh, I missed, oh yeah, they could never be 4, right. This one can't be 7, sorry. These two can't be 7 because of the 7 in the row. And so these are actually somewhat limited. We don't quite have a 2, 6, 8 triple. And now we can move on from here. And I'm going to keep this cell highlighted orange, just sort of mark it as special, because that's still going to be our focus, because that's the one cell that our 3 fin jellyfishes did. So you could have just used the 3 fin jellyfishes and come to the same conclusion, but I think that this set argument is also very fun, and it does all 3 of the fin jellyfishes at once and gives us a little bit of extra info, although I believe the 3 jellyfishes also did these same eliminations of 3 and 4 in this row. We just haven't marked it. So it has the same effect. It's just a more interesting way to see that, maybe. Now for the next step, I am actually going to need to do more coloring. So we don't need to call out this cell quite yet. But what I'm going to do is adjust this set a little bit. Because you know, when you're trying to solve these, you're probably going to be playing around with the sets to see what you can find, and there's really no way around that. But one thing that we don't really like is the situation. We've gotten everything we could out of this particular set. We don't like the situation where this particular cell is double counted. So let's just remove this from the blues, which re-adds these to the reds, removes these blue cells, and makes this back to blue because it's no longer double counted. And so now if we count up, we have 5 sets of 1 to 9 from the red and 4 sets of 1 to 9 from the blue. So we are imbalanced at this point. And one thing we can actually, it's going to make us more imbalanced, but one thing we can kind of notice is that in the blues, if we were to get rid of this column from the blues, we would no longer have a 5 in the blues either. And so we may be able to make use of the fact that 5 would be missing from the blues. So as long as when we add more things, we aren't adding any given 5s, we can kind of talk about 5s as well as the 1, 3s, and 4s. And so what I'm going to do is I'm going to remove this column from the blues, which re-adds these parts to the reds. And so this one could have been drawn by drawing 5 rows of reds and 3 columns of blues. So we're very imbalanced now. And what we're going to do is we're going to actually just make this 3 and 3. So if we look, we can remove these 2 rows from the reds, which puts them back in the blues. And we haven't given the blues any given 5s or 1, 3s, or 4s. And so we are still in the situation where the blues don't have any given 1, 3, 4, or 5, and the reds do have given 1, 3, 4, and 5. And so what we can do is we can say, well, the blues must have a 1, 3, 4, and 5. and there's only 5 open cells to receive them. So we have 1 degree of freedom. 4 of these cells will have 1, 3, 4, and 5, and one of them is kind of a free, free to be anything else from the reds. So we're not quite there, but let's look at this cell that was affected by our, our fin jellyfishes or our previous set work, whichever one you want to talk about, this 2, 6 here. So let's think about these 3 cells here. What would happen to these 3 cells if they didn't have a 1, 3, 4, or 5 in them? And in fact, they can't have a 1, so we can really just talk about 3, 4, and 5. But what would happen if they did not have any 3, 4, and 5 in them? So what we may want to do is we may want to mark what this cell can be. So it can't be a 1. It can be 2, 3, 4. It can't be 5. Can be 6. Can't be 7, 8, or 9. This is 7, 8, and 9. So if we didn't have a 3, 4, or 5 in these 3 red cells, they would make a 2, 6, 8 triple, and this cell would have no value. So to put that another way, we have to have an additional 3, 4, or 5 in these 3 red cells, somewhere in these 3 red cells, and actually it can't be here, so it's in one of these 2. Either this is a 3 or a 4, or this is a 5. And so we actually do have another 3, 4, or 5 in our reds that removes our degree of freedom. And so in order for the blues to also have the 1, 3, 4, and 5 with a repeated 3, 4, or 5, they have to go in these blue cells. So we can actually just mark those blue cells as 1, 3, 4, or 5. And we can just if you want, you can remember that there's definitely only 1, 1 in them. And then one of the 3, 4, or 5s is repeated. We don't know which yet. And so there's a few other things that we can detect from this, which is because the blue cells could only accept one more 1, 3, 4, or 5, that means that aside from the one of these red cells that is a 3, 4, or 5, the other ones cannot be 3, 4, or 5, because if they were, they would not fit in the blue cells anywhere. We've already used all 5 of our open blue cells. So the other 2 are not 3, 4, or 5, which means they're from 2, 6, or 8, which with this cell here forms a virtual 2, 6, 8 triple. And so what that means is the rest of these white cells cannot be 2, 6, or 8. So let's just pencil mark what they can be. So they can be 1, they can't be 2, they can be 3, 4, they can be 5, they cannot be 6, they can be 7, and they cannot be 8 or 9 because there's a 9 in the box. And then we can actually just clean this up a little bit. This one can't be 5, can be 1, 3, 4, 7. This one can't be 4 or 7. This one, what does it see anything? 1, 3, 4, 5. Yeah, these 2 see a 5. This one sees a 7. And so now I can get rid of my, we're fully pencil marked in this box, so I can just get rid of my little corner marks there. So that is already very good progress. And in addition to that, the last thing that we can say is that not only these reds, but none of the other reds can have 1, 3, 4, or 5 in them. They must be from whatever these blue givens are, which is 2, 6, 8, and 9. 2, 6, 7, 8, and 9. So I can just go into all of these remaining red cells, other than the ones in box 7, and I can mark them as 2, 6, 7, 8, 9. And of course, we can do more eliminations here. So this one can't be this one can't be 7 or 8 from the box. This one can't be 8 or 7 or 6. So it's a 2 or 9. These can't be 8. These can't be 7 from the row. This also can't be 8. All of these can't be 9 from the box. This can't be 8 from the column. This can't be 7. And I think that's it. Hopefully I got every elimination. If not, I will discover that in a second. And so now what we can see is that the remaining, this forms a 2, 6, 7, 8 quad. So these must be a 1, 3 pair. We can also see that in column 2, if I were to pencil mark the rest of this column, what can these be? They can be 1, 2, 3, 5, 6, 8. And in the box, sorry, we can't be 5 or 8. So it's actually 1, 2, 3, 6. This one sees a 2, and this one sees a 2 and a 6. And so now we actually have a 1, 3 pair in column 2. And so this is a 6 and this is a 5. Now that this is a 5, we have a 2, 6, 8 triple, and this also can't be 6. This is a 2, 6, 8 triple, which removes 2 and 6 from this cell, making it a 3, 4. And also we know that 6s are in one of these two, so that eliminates 6 from here. And this 6 eliminates 6 from here, meaning that 6 is in one of these two cells. I may as well also mark here that these two 9s look up along with this 9, and that does mean that there are two 9s here. We could have done that at the start of the puzzle. Didn't need to. And we end up with these markings here. So from here, there's several ways you could move forward, but I'm going to pick an interesting way to do it. So first, I'm going to get rid of the coloring because I think it's just going to get in the way of scanning. We no longer need those sets or this special cell because we're kind of doing a more standard solve here. But an interesting way to move forward from here is first to notice in this row, where do 1, 4, 5 go? Well, they can only go here because none of these other cells can be 1, 4, 5. So that's a hidden triple 1, 4, 5. And then now what we can say is where do 2 and 6 go in this row and this row respectively? Well, 2, we have these 3 given 2s that see into here, and then there's givens in the rest of the row. So 2 is limited to these 2. I'm going to mark that across boxes just for visualization here. I normally wouldn't. And then in this row here, we're actually fully marked. You can see that 6 can only be in these two cells, and that's because of the 1, 4, 5 triple, as well as these 6s limited in the box and this 6 in this box. So 6 is limited here, 6 is limited here, 2 is limited here, and 9 is limited here. So what would happen if I were to place a 6 in this cell? Well, that would, because of our markings, let me mark 6 here as well. So it's kind of hard to mark that doubly, but if you remember, 6 had to be in this row, one of these two, 2 in one of these two, 6 in one of these two, 9 in one of these two. So if I put a 6 here, that's going to force 2, 9. And then where does 6 go in this row? It had to be in one of these two. And now neither of them can be 6 because there's a 6 here, right? Let's just visualize it. 6, 2, 9. There's a 6 here eliminating the 6 from here, and there's a 9 now occupying this cell. Can't be both a 9 and a 6. And so that breaks the puzzle. So now we can fill a 2 here, and that just finishes off this row here. So we can do these eliminations. And that eliminates down here. That forces a 2 into here. This is 6, this is 8. That finishes this triple. And now we have a 1, 3, 4 in the box, or to put another way, where does 7 go? 7 must go here. And so now if you remember, this cell here that we just filled with a 7 was part of our finned jellyfishes that we did at the start. And it's no longer a fin because it's a 7 now, which is not 1, 3, or 4, which were our jellyfishes. So if we remember, our jellyfishes were here. If I just highlight that green. And I know that's 5 rows, but the 1, 3, and 4, again, there's always a row missing for each of those. And so now what we can do is we can look at this cell, which clearly sorry, if we fill this 2 here, let me just really quickly do that. This is a 2. Now it's really easy to see that this is 1, 3, 4, or 5. But remember, this row is active in all 3 of the jellyfishes for 1, 3, and 4. So it can't be 1, 3, or 4. And so it must be a 5. So that places that 5 there. And that's really the only important elimination from that. And from here, there's really lots of ways to do the solve. 5c's up here, so now 5 must be in one of these two. This is no longer 5. And we can just solve this normally from here. There's nothing particularly difficult afterwards, mostly hidden singles. So let's just take a look at what we can see. So we just placed this 5. That places another 5 here. Let's see if we can finish off those 5s. This 5 looks up here. And here. I'm not seeing anything with that. Oh, and these 5s look over. So there is a 5 in one of these two. And what else can we see? So we are almost done with 2s. These 2s look up here. So you can see, where does 2 go in the box? We already marked non-2s here, and this 2c's over here. So this is a 2. 2c's down. Oh, we already have a 2 here. This 2c's here. That fills a 2 here. And now the 7 gives us this 9 and the 6. This 6 C's down here, along with this 6, putting a 6 in this box. That gives us this 9. This could never have been a 1. And the remaining cells here are 3, 4, and 6. This can't be a 3. This is also 1, 3, 4. And so now we have a 1, 3, 4, 5 quadruple in the row. So the remaining cells are 2, 6, 8, and 9. This can't be 6 or 8. This can't be 9 or 6 or 2, so that is an 8. And then this is not, neither of these are 2, so that forces a 2 here. This isn't a 9, so that's 6 and 9. Now where does 8 go in this box? It can only go here. That's from these two 8s. And I believe that, yeah, the 8s are done. So what's remaining in this is 1, 3, 4, or 5 as well. These can't be 1. This can't be 5. This can't be 3. This 6C's down here. This is 4, 3, and 6. These two can't be 3. This 4C's over, leaving a 1 or a 3 in this cell. And then this is a 3 or a 4. In this box, we need 1, 3, 4, 5 as well. These can't be 5. In this box, we need a 1, 3, 4, or 9. And this can't be 9, so the 9 can only go here. In this box, we need a 1, 4, 5, and 9. The 9C's here, so that places this 9, and that does finish the 9s. And this cell can't be 4, neither can this one. And here we have a 1, 3 pair, so this is 5, this is 4. That gives us a 3, 1, 3, 1, 3, 1, 4, and 3, 4, 1. And we're basically done at this point, just finishing up. So this can't be 4, this can't be 4, this can't be 4. And so this is 5 and 1 from the 3 in the box. This is 3. These can no longer be 3. This can't be 3 either. So that leaves just here for 3. That was the last in the box. This one can't be 4. Neither can this one, leaving 1, 5 pair. So this is placeable. It looks like it's a 3 as well. And then this cell here is a 1, 4, or 5, but it can't be 4 or 5. So this is 1, 5, and 4. This is 1, 4. This C is a 4 and a 5, so that's 1. This C is a 1, that's a 4, and this is a 5. And we click check, and there we go. We have solved the puzzle. So I hope you enjoyed that. Definitely some very interesting stuff using set theory on this puzzle, which makes it solvable when really I don't think you really could without it. So I think that's a really good demonstration how even in a classic Sudoku, set theory can really come in handy for these difficult puzzles. And even if the puzzle's not difficult, sometimes it can be fun to play around with that. But definitely enjoyed that. Thank you, Philip, for providing the solve path. I know you're a busy man, and people were asking for the path, and you're like, well, I'll try to find time. So I'm glad you did. And to everyone else, until next time, thanks for watching.